We will go through a small demo now to have a quick hands-on. Once you are in projects page in your OCI data science, click on your working project. In my case, this is test.ts. You can see on the left hand side, there are different resources such as notebook sessions, jobs, models, model deployments. Go ahead and click on model deployments. You can now click on create model deployment. In there, make sure you are in the right compartment. In my case, this is OCI data science compartment. You can enter a unique name for the model. It has a limit of 255 characters. If you don't provide a name is automatically generated for you. So let's go and enter a name here. I am putting test model deploy in my case. You can also provide a description for the model deployment. So this is to test model deployment. You can then select an active model to deploy from the model catalog by clicking select. In my case, you can see I already have an active model RF classifier. So I'm going to select that one and submit. Once you select the model, you can go ahead and select the VM shape and the limits you want to apply to your model deployment. So I'm going to select the compute shape. So I'm going with number of OCPUs 1 and memory 15. You can also select the number of instances for the model deployment to replicate the model on. The more instances you have, the more load the deployment can handle by distributing the requests across the instances. So let's go ahead and select 2. Hit the submit. You can also enable the logging. It's an optional configuration. So go ahead and click on select. You can see the access logs and the predict logs here. So access logs, it captures detailed information about request, and as we discussed earlier, predict logs, it captures std out and std error from the predict Python code. So go ahead and select the log names and then hit submit. So in the show advanced options, you can also set the load balancing and tags there. So basically you can select the load balancing bandwidth in Mbps, or you can also use the 10 Mbps by default. So the recommended way to do this is the formula which we discussed. This is a payload size in kilobytes multiplied by estimated number of requests per second and then multiplied by 8 divided by 1024 KB. So for example, if the payload is 124 kilobytes and you estimate 120 requests per second, then the recommended load balancer bandwidth would be 1024 multiplied by 120 multiplied by 8 and divided by 1024. And since we always add an extra 20% to allow for estimation errors and sporadic peak traffic, I'm going to multiply it by 1.2. So, and that comes to be 1152 Mbps. For our case, I'm just going to leave at 10. Hit on the create. It should take some time for model deployments to be completed. And now you can see that the status for your test model deploy will change to the active. So let's go ahead and click on the test model deploy. Here on the screen, you can see the model deployment information, such as the general information, the compute, and the models, what is the deployed model for you. Also different tags associated, in this case the owner for this model deployment. You can also check different metrics associated with this test model deploy. So right now you can see success rate, request count. There is some activity regarding to CPU utilization, memory utilization, and so on. So you can also go ahead and check the logs. You can see that you have 2 log categories enabled for you for the predict and access. You can also see the work request for the create model deployment, and you can see that status is succeeded with 100% complete. You can also invoke your model as an HTTP endpoint using this link. You can also call your model from the OCI CLI using this command, or you can call your model from OCI Python SDK or using Java SDK. You can also deactivate or reactivate your model deploy, and you can even delete your model deploy once you're done with your model deployment.
First of all, let me congratulate you for reaching so far in the course. My name is Hemant Gahankari and I'm a Senior Principal Training Lead at Oracle University. Hugging Face library allows us to build pipelines for various tasks like computer vision, natural language processing, and many others. Support for deploying Hugging Face pipelines onto the OCI data science was added recently. I'll walk you through one small example of deploying Hugging Face pipeline onto the OCI data science. As you can see, the transformers library is imported here. We build a pipeline using the transformer model here. Then we wrap that pipeline using the Hugging Face pipeline model. Then we prepare the model artifacts using the .prepare method. We verify the deployment using the .verify method. We save the model into the model catalog using .save method, and then finally we can deploy the pipeline using .deploy method. I'll recommend you to go through the documentation. Thanks for watching.
Welcome to the demo, model deployment using TensorFlow model class in ADS. Here we will see how to register your model with Oracle Data Science Service through Accelerated Data Science Library. ADS has a set of framework specific classes that take your model and push it to production with a few quick steps. The first step is to create a model serialization object. This object wraps your model and has a number of methods to assist in deploying it. There are different model classes for different frameworks. For example, if you have a PyTorch model, you would use the PyTorch model class. If you have a TensorFlow model, you would use the TensorFlow model class. So for our demo, we will showcase the deployment using a TensorFlow model class. After creating the model serialization object, the next step is to use the prepare method to create the model artifacts. The score.py file is created and it is customized to your model class. You may still need to modify it for your specific use case, but this is generally not required. The prepare method also can be used to store metadata about the model, code used to create the model, input and output schema, and much more. If you make changes to the score.py file, call the verify method to confirm that the load model function and predict functions in this file are working. This speeds up your debugging as you do not need to deploy a model to test it. The same method is then used to store the model in the model catalog. Call to deploy method creates a load balancer, and the instances needed to have an HTTPS access point to perform inference on the model. Using the predict method, you can send data to the model deployment endpoint and it will return the predictions. So these simple steps together will take your trained TensorFlow model and pushes it to the production with just a few lines of code. Here you can see the ADS library used to interact with the Oracle Data Science Service. The logging module is used to control the logging output. The OS module provides a way to interact with the operating system. The pandas module is used to work with data in a tabular format. The temp file module is used to create temporary files and directories. Again, TensorFlow module is used for building and training machine learning modules. TensorFlow datasets module is used to access pre-built datasets. So fashion administers one of the pre-built datasets. Again, the warnings module is used to suppress warning messages. Next, you see here the code imports several modules from the ADS library. These modules are used to interact with the Oracle Data Science Service. Model catalog is used to create and manage models. Use case type is used to specify the type of machine learning use case being used. Dataset factory is used to create and manage datasets. TensorFlow model is used to create and manage TensorFlow based models. RM tree here is used to delete directories and their contents. Finally, this code sets up authentication using the Oracle Data Science Service. The choice of authentication method is resource principal here. So overall, this cell blocks sets up the necessary libraries and authentication to interact with the Oracle Data Science Service using Python. So the fashion administ dataset, it consists of a training set of 60,000 examples and a test set of 10,000 examples. Each example is a 28 by 28 grayscale image associated with a label from 10 classes. So moving on, the next section of the code loads the fashion administ datasets and displays some of its images using matplotlib. So let's run this. So again, this code uses a TensorFlow to load the fashion administ dataset. You can see this is how the dataset looks. So this next cell creates a TF model class that loads in the fashion administ data using a public internet connection. The data is then scaled to be between 0 and 1. And again, to reduce the computational time needed to generate the model, only the first 10,000 training samples are being used. The different layers of this model is being defined in this first method called training. The first layer is a flattened layer, which flattens the input images into a one-dimensional vector. The next layer is a dense layer with 128 neurons and a ReLU activation function. The next layer is a dropout layer, which randomly drops some of the neurons during training to prevent overfitting. The final layer is another dense layer with 10 neurons, one for each class in the fashion administ dataset. The code then defines a loss function and compiles the model. Again, the loss function used is sparse categorical cross entropy, which is appropriate for multi-class classification problems. The model is then compiled with the Adam optimizer and accuracy as metric. Finally, the model is trained on the reduced training set. So you can see here the loss was 0.7899 and accuracy is 0.7235. Once the model has been trained, you can use the predict method to make predictions on a subset of the test dataset. Each prediction outputs 10 values because there are 10 nodes on the output layer. You can see as defined here. The node with the highest value is the digit that the model predicts. Now keep in mind, our end goal for the demo is not to work on improving the baseline model created above, but to learn how to deploy this model using the TensorFlow model class. So let's continue with the deployment steps. So the TensorFlow framework makes it easy to deploy a TensorFlow model into production. The TensorFlow model constructor takes a TensorFlow model and converts it into a TensorFlow model object. Again, to deploy the model into production, you must prepare the model artifact, verify that the artifact works, and save the model to the model catalog and then deploy it. ADS provides a number of methods that greatly simplify the model deployment process. Again, it also provides the summary status function that provides a data frame that defines the steps status and detailed information about each step. So now let's see the steps to create the model artifact. In this notebook, this sequential object is created. The TensorFlow model constructor takes this sequential object along with the path that you want to use to store the model artifacts. A TensorFlow model object is returned and it is used to manage the deployment. This next cell here creates a model artifact directory. This directory is used to store the artifacts that are needed to deploy the model. It also creates the TensorFlow model objects. On running this cell, you can see this artifact directory is being created into a temporary directory. As mentioned above, summary underscore status method of the TensorFlow model class is a very handy method to keep track of the progress that you're making in deploying the model. It creates a data frame that lists the deployment steps, their status, and details about them. Again, the next cell returns the summary status data frame. It shows the initiate step has been completed. So as you can see here, it shows you different steps in this data frame: initiate, prepare, verify, save, deploy, predict, and again their respective status and details. Now we have initiated the model. Let's move on to the prepare step. So the prepare step is performed by prepare method of the TensorFlow model class. It again creates a number of customized files. These are the files. So out of these 5 files, the first file is input underscore schema. So this is a JSON file that defines the nature of the features of the sample data. The second file is model.h5. This is the default file name of the serialized model. You can change it with the model underscore file underscore name attribute. So again, by default, the model is stored in an h5 file. So h5 file is a data file saved in the hierarchical data format. It contains the multi-dimensional arrays of this data. So the third file is output underscore schema.json. So again, this JSON file defines the nature of the dependent variable in the sample data. The fourth file is runtime.yml file. This file contains information that is needed to set up the runtime environment on the deployment server. Again, so the information about which conda environment was used to train the model, again, the what environment should be used to deploy the model. This type of information is stored in this particular file. The fifth file is score.py. So it's a Python file which contains the load underscore model and predict function. The load underscore model function understands the format the model file was saved in and then loads it into memory. The predict method is used to make inferences in a deployed model. Again, you can see here the conda environment is being defined for the inference and the training. Let's see the summary status again by invoking this particular method to show that prepare step has been finished. And again, what tasks were completed. So you can see here initiate step and the prepare step, they both are done. And the model has been initiated. Again, the runtime.yml file, score.py file, those has been generated. Again, the model is there and the metadata also has been populated. Here you can see these were the 5 files which we talked about. Once the artifacts have been created, there are a number of attributes in the TensorFlow model object that provide metadata about the model. The runtime attribute details the model deployment settings and model provenance data. So let's see the information about that. So now you can see the artifact version here. Again, deployment with this particular conda environment, which has the conda environment name, the type of the service, again, the Python version. Similarly, you have details about the model provenance here. Underscore input attribute provides metadata on the features that were used to train the model. Again, you can use this information to determine what data must be provided to make model inferences. Again, each feature in the model has a section that defines the data type, feature type, name, and if it is required or not. The metadata also includes the summary statistics associated with the feature type. Again, you have metadata underscore custom attribute, which provides custom metadata that contains information on the category of the metadata, description, key, and value. So you can see here the details. Again, metadata underscore provenance attribute contains information about the code and the training data that was used to create the model. This information is most useful when you are using a Git repository to manage the code for training the model. Again, the last attribute is metadata underscore taxonomy, which is a key value based store that has information about the classification or taxonomy of the model. Again, this can include information such as the model framework, use case types, different hyperparameters, and so on. So this concludes our prepare method. So we will now move on to verify method. So again, as I have mentioned previously, if you modify the score.py file, which is the part of model artifact, you must verify it. Again, it allows you to test those changes without having to deploy the model. This allows you to debug your code without having to save the model to the model catalog and deploy it. So basically, the verify method takes a set of test parameters and performs the prediction by calling the predict function in score.py. Again, it also runs the load underscore model function. So you can see here now the model was successfully loaded. Again, you can check and conclude the verify method using summary underscore status method. So now let's run the summary underscore status method. And now you can see here again, like these 3 steps being done, their status, and again the details. So you have basically tested locally predict method from the score.py. That the save step is available now. And so once you are satisfied with the performance of the model, and we didn't go into improving the model, but if you are satisfied with the performance of the model and have verified that the score.py file is working, you can save the model to the model catalog. You do this with the save method on the TensorFlow model object. So basically, this bundles up the model artifact that you have just created and deploys it to the model catalog. It will also return you the model OCI. I mean, which is basically a unique identifier. So let's run this. You can see here the model is being loaded from model directory, and it was successful. So this concludes now this save step. You can I haven't included, but you can again check now the tf underscore model dot summary status. So it will show you now that these steps are being done, the related details. Now the deploy step is available now. So you can also check the model catalog and confirm that whether model was saved or not. So let's go back to the project details, and you can see here in the models, you have this demo FMST TensorFlow model being in active status now. So this is the model we just created and save into the model catalog. Moving on, so the next step is deploy, which is available. So when the model is in the model catalog, you can use this method of the TensorFlow model object to deploy the model. This method allows you to specify the attributes of the deployment, such as the display name, description, instance type, and count. Again, the maximum bandwidth and login groups. So we have just passed the display name here as a parameter, nothing else. So let's deploy this particular model. This step might take some time. You will also see a progress bar here while the model is being deployed. So now again checking the resources section, you can see here my model is in active status now, and this is the name of the model. Again, you can confirm the same using the summary underscore status method, which will show you that the model is active and the predict method is available. So moving on to the last step, in the create a TensorFlow model section, you earlier used the model.predict method, where model was an ADS model object. I mean, you basically did the inference using the local model. So I will just show you. So basically, this is the step which I'm talking about. So you did it locally here. So now that the TensorFlow model has been deployed, you can do the same thing using similar syntax with the dot predict method on a TensorFlow model. So basically, after the deployment is active, you are calling the predict function on the TensorFlow model object to send request to the deployed HTTPS endpoint. So let's do the prediction. Now we have almost concluded our demo. So let's do the last step, which is cleanup. So basically, our notebook created a model deployment and a model, and this section will help clean those resources. And again, this is a very important step. You must clean the resources. Once you're done. Also, the model deployment must be deleted before the model can be deleted. So basically, you need to delete this model deployment before you go on and delete the model. So so we are going to use delete underscore deployment method on the TensorFlow model object again. So let's run this. So it will take some time, but now you can see and confirm up here that the model deployment has been deleted. So you can again check the summary status method. You can see the deploy in the deploy step. The model deployment has been deleted. Now we will follow the same step and we will delete the model itself from the model catalog. So let's run this. So now you can see this one was quick and the model has been deleted. So you can confirm the same here from here. So it just changed. Then this next cell removes the model artifacts which were stored on your local drive, so on your data science directory. So let's delete those. So this now concludes our demo for model deployment using TensorFlow model class in Accelerated Data Science Library. Hello and welcome to this lesson on Large Language Model Training and LangChain Integration, a part of OCI Data Science course. OCI Data Science Jobs provides fully managed infrastructure to enable training of a large language model at scale. It supports both full parameter fine-tuning and parameter efficient fine-tuning. With ADS, you can start the training job by taking the source code directly from GitHub with no code change. To fine-tune the model, you will first need to access the pre-trained model. The pre-trained model can be obtained from Meta or Hugging Face. You can then define the training job with ADS Python API. You can then create and start the job run using an API call and also stream the job run outputs. The job run steps will set up the Conda environment and install additional dependencies, fetch the source code from GitHub and check out the specific commit. It will run the training script with the specific arguments, which includes downloading the model and dataset. And then it will save the outputs to OCI object storage once the training finishes. During training, there is no need to specify the number of nodes or the number of GPUs. ADS will automatically configure that based on the replica and shape you specified. Once the fine-tuning is finished, the checkpoints will be saved into OCI object storage bucket as specified. OCI Generative AI provides text generation, summarization, and embedding models to be used in LangChain with ADS. By default, the integration uses the same authentication method configured with ads.setAuth method. Optionally, you can also pass the auth keyword argument when initializing the model to use a specific authentication method for the model. For example, to use resource principal for all OCI authentication.
In this demo, we will see how to deploy a LangChain-based retrieval augmented generation application to OCI data science. So let us begin. We will begin with the import of the necessary classes. We will authenticate using resource principal. We'll create embedding using generative AI embeddings class and our model using generative AI class. We'll create a text loader and we will load a document. We'll also split the document and we'll create a vector data store using the documents and embeddings that we created earlier. We will create a retriever using our vector database. We will create a chain using retrieval QA class and we will pass our LLM and retriever to it. We'll create a temporary directory and we will use a chain deployment class to create our model. We'll pass the created chain and the temporary directory to it. We will prepare the model artifacts using the model.prepare method. Let's also verify the model that is prepared. So as we can see here, the model artifacts are created and now we can verify our model. We are going to pass in a prompt to it, what is AI Foundations course, and we can see the response to our question here. Now we can save the model and finally we can deploy our model. Model deployment usually takes about 10 to 15 minutes. We can see that our model is deployed now and we can call upon the predict method of the model to get a response from the model. We are going to pass in a question, who are instructors for AI Foundations? This is a very specific question and answer to that question is available only in the text that we had provided. So let us ask this question and see what response we get. So as we can clearly see, the instructors for the Oracle Cloud Infrastructure AI Foundation course are Hemant Gahankari, Himanshu Raj and Nick Comiso. So this was a very specific information which was available only in the text that we had provided. So we can conclude that our model is deployed successfully to OCI data science and we can integrate that model into our LLM application. Data science operators is a recently introduced feature of the OCI data science. Essentially, operators are a pre-packaged set of libraries suitable for a specific task like forecasting, anomaly detection, or detecting personal identifiable information. These are designed to be low code and can be executed in a variety of environments, including OCI Data Science Notebook. Operators can be easily invoked through a CLI. There are three types of operators available to use. Forecasting operator can be used with time series data to predict future values. For example, given the weather data for last 5 years, predict temperature values for the next week. Anomaly operator can be used to detect and flag anomalous movements in your data. For example, in a given set of data, a few values may not be consistent with the rest of the data and need to be identified. PII operator can be used to detect and redact personally identifiable information in a given data. For example, email, employment history, and so on. Let us see how to use these operators in a demo. In this demo, we will see how to use data science operators. So before we begin using the operators, let me just walk you through the documentation for the operators. So we are into the documentation of Oracle ADS And within this documentation, you will find a section on low-code AI operators. So here are various sections: what are operators, getting started. Then there is more specific information on specific operators like forecasting, anomaly detection, and PII. We will begin with using the forecasting operator. So if we go to the installation of the forecasting operator, what we will find that there are a variety of options for installing the forecasting operator. But what we are going to do is we will be installing the operator and we will be using it through the Conda environment. So for that, we have to go to the notebook session and use the environment explorer. So let's do that. So we are into the environment explorer of a notebook. There is a pre-created AI forecasting operator here. So let's see what is inside this operator. So here is an AI forecasting operator. It consists of multiple libraries, as you can see. All these libraries will be used by this operator to train models using the data that is provided and predict the values. We can install this operator using this particular command. So we can just copy and paste this command into the terminal. So we can open a terminal here and just from the environment explorer, copy this command and install this Conda environment. But in our case, the Conda environment for forecast and anomaly detection is already pre-created. So we'll be using this particular Conda environment to use our operator. We are in the quick start section of the forecasting operator. Now what we have to do is we have to use this initialize command here. So we can copy this command and come back to our terminal over here. And we can paste this command here. And let's see what it does. So as you can see, we got this my forecast directory over here, which was the output directory in this command. Now let us click on this directory and we see that multiple files have been created here. These are all YAML files here, and these YAML files are basically configuration files which allow us to configure the operator before running the operator. Now, multiple YAML files are provided so that we can run the operator into multiple environments. Now, for running it locally, we can just open this particular YAML. We are into the my forecast directory over here, and we will edit the forecast.yml. And we can see that there are few parameters which are already configured into this YML. But what we are going to do is we will take the content of this forecast.yml from our documentation. So we are going to copy this particular content and put it there. So our forecast.yml is configured now. So we will activate our Conda environment. So now our Conda environment is activated. So let us switch to the my forecast directory. Now we are into the my forecast directory. Next, what we'll do is we will run our operator. So for running the operator, we can use this particular command over here. We'll copy it. We'll go back to our terminal and paste the command over here. It'll take a few minutes for the operator to run. So we can see here that the outputs have been successfully generated and placed into the directory results. And we can see this results directory over here. So there are multiple files which are created here. One is a forecast.csv. Then let's check on the report.html. So we can see that the forecast report is ready. And you can see first 10 and the last 10 rows of the data. You can also see the summary of the data, and this is the forecasted data overlaying the historical data. The process to use the operator is very simple. First, you install the appropriate conda environment. Then we initialize the operator. We activate the conda environment, and then we can edit the forecast.yml to configure the operator the way that we want to. To learn more about how to configure the YML, you can refer to this YML schema section. And then finally, we just run the operator. Similarly, to use the anomaly detection operator, we can install the appropriate conda environment. We can activate the conda environment, and then referring to the quick start, we can initialize the operator and we can run the operator. So similarly for PII also, you can see that this is the command to install the PII conda environment, and this is the command for activating that conda environment, and this is the command to initialize the operator, and this is a command to run the operator. So all these three operators are very useful to run the offline data analysis for forecasting, anomaly detection, and personal identifiable information. Thanks for watching. AI Quick Actions is a recently introduced feature of the OCI data science. It allows you to quickly deploy pre-trained large language models to OCI data science. The deployed models can be used to integrate with your applications. Apart from deploying the models, you can also fine-tune the out-of-the-box LLMs by providing a custom dataset. The deployed models can also be evaluated using a given dataset. AI Quick Actions are available to use from the OCI Data Science Notebook. You can refer to the OCI Data Science documentation for setting up required policies to enable AI Quick Actions in the notebook. Let us see how to deploy a LLM to OCI Data Science in a demo. So we can see here that we are inside a OCI Data Science notebook session, and we are able to see this AI Quick Actions button over here. So let's click on it. In the AI Quick Actions page, we are able to see that there are three tabs: Models, Deployments, and Evaluations. In the Models tab, we are able to see the out-of-the-box large language models which are available for us to deploy. Let's go to the deployments. We already have deployed a model over here, but I will show you how to create a deployment. So let's click on the Create Deployment. We can give a name to a deployment. We can select the out-of-the-box model. So let us select Mistral 7B Instruct version 0.02. And we can select a compute shape here. So we will keep this as VM GPU A10.1. And we can also select a log group so that if there are any issues during the deployment, they will be logged. And then we just click a deploy button. So in our case, we already have deployed large language model and it is active. So let's click on the deployed model over here, and we can see that it is in an active status, and this is the endpoint that we can use if we are calling the model from the API. We can also test our model using this section of the page. We can adjust the model parameters, various model parameters, and we can type in our prompt. Say for example, let us say tell us about Las Vegas, and let's click on generate. And here is the response, as you can see.
Hello, my name is Ludmil Pelov and I'm a product manager in the Data Science and AI Services team. In this class, we are going to talk about MLOps and its use in Oracle Cloud. MLOps is machine learning operations and are based on DevOps principles and practices that increase the efficiency of workflows and improves the quality and consistency of your machine learning solution. MLOps usually refers to the standardization, streamlining, and automation of machine learning lifecycle management. ML assets are treated like other software assets within the iterative, continuous integration, or continuous delivery environment. Machine learning models are deployed alongside the services that wrap them and the services that consume them as part of unified release process. MLOps is a set of technologies and practices to rapidly deploy and manage scalable and governed machine learning applications in production environment. MLOps pulls heavily from the concepts of DevOps, which streamlines the practices of software development and updates. You may be familiar with the DevOps workflow diagram, which is similar to the MLOps diagram. The DevOps lifecycle includes practices like building, testing, continuous deployment, and monitoring that apply to machine learning operations practices as well. In MLOps, continuous integration refers to the validation and integration of new data and machine learning models, and continuous deployment refers to releasing that model into production. Continuous training is unique for MLOps and refers to the retraining of ML models for redeployment. Retrained models should always undergo a process that assures the quality of the model. While DevOps and MLOps have quite a bit in common, there is one critical difference. Whereas software code could be relatively static, data is always changing. That means machine learning models are constantly learning and adapting to new inputs. This drift in data is why the continuous retraining of machine learning models is so critical. If the model isn't updated to reflect the new data, its predictions could become less and less accurate. Due to this degradation in the model's performance over time, it is important to retrain the model on new data as quickly as possible. This is where the continuous integration in MLOps provides great benefit. At the same time, every retrained model should be cross-validated and undergo a process that assures the quality of the model predictions. Whereas DevOps automates software code updates and releases through continuous integration and continuous deployment, or CI/CD, MLOps adds the automation of model adjustments through continuous training. There are multiple levels in the automation of MLOps workflow as your process continues to mature. The first step is the solidifying the manual implementation of the machine learning processes as basis of what will ultimately be automated. This is an experimental, iterative state where data preparation, model training, and validation are done manually and often using rapid application development tools like Jupyter Notebooks. The next step is automating the machine learning pipeline where the model training and validations are executed automatically and continuously. Incoming new data triggers a new model retraining and validation processes to ensure the model is optimized. The final step is the CI/CD pipeline automation, or the true ML ops. This is where the data, machine learning model, and training pipeline are automatically built, tested, and deployed. At this stage, machine learning models are automatically and continuously deployed into a core software system or service through triggers based on changes in data, monitoring events, or calendar intervals. Continuous monitoring checks production data and model performance metrics, which are bound to business metrics. If model performance degrades, it can trigger a new training and validation process. This is the MLOps architecture, which shows the life cycle from data ingestion to deploying the model in an application to the end user. Data from businesses or scientists is sent into the Jupyter notebooks for model development. New data inputs or notebooks triggers the OCI DevOps CI/CD pipeline. The DevOps build pipeline runs the training job and sends the output to the model catalog. The completion of the build pipeline triggers the deployment pipeline. The machine learning model is deployed for testing. The model is tested on an internal endpoint. If the model is approved, it is deployed for production. Finally, the model is sent to the end user application. Hello, my name is Ludmil Pelov. I'm a product manager in the Oracle Data Science and AI Services team, and in this lesson we are going to learn about OCI Data Science jobs. The Jobs service sits inside the Oracle Data Science service and is an essential enabler for MLOps on Oracle Cloud. It provides the on-demand infrastructure required to run processes when needed and helps optimize cost. Jobs lets you define and run repeatable tasks or set of tasks on fully managed infrastructure that it's provisioned only when the job is run. The job service enables custom tasks so you can apply any use case you may have, such as data preparation, model training, batch inference, and many more. It can automate a single step or several steps in an IO MLOps lifecycle depending on the size of your project. A complex project may have a separate job for each step in an MLOps lifecycle, where a smaller project may combine them all into one or a few jobs. There are several benefits to using jobs for your MLOps or batch processing projects. They are fully managed, so you don't need to operate third-party batch processing solutions or install or manage software or servers. The service reduces the complexity of provisioning, managing, monitoring, and scaling your batch jobs processes. They're also integrated as OCI native service, so you can leverage all the Oracle Cloud capabilities like databases, networking, security, and more. This makes it easy to securely process data to or from Oracle Cloud. Finally, they are provisioned on demand, so you can select resources based on processing requirements. Infrastructure is automatically deprovisioned on the processing end, and you are only charged for the resources used during the duration of the job. There are two key concepts with data science jobs: the job itself and job runs. A job is a template that describes a task and specifies details about relevant components like you see on the left. It defines the infrastructure and the actual use case artifact. A job run is a single execution of a job, usually with customized parameters assigned to it. A job can have several job runs associated with it. Let's look at each one in more detail. A critical element of a job is the job artifact, which contains instructions for the job to be run. It is immutable and cannot be modified after it is uploaded to a job. Environment variables or CLI arguments to jobs can also be included. These optional items can be similar for all your future job runs, or you can override them in each job run. You must also specify the compute shape the job runs on. Unlike the job artifact, this can be edited in the job and between job runs. For example, if you decide to execute a job run on more powerful shape, you can edit the job compute shape and then start a new job run. Finally, you can select logging options. as well as the size of the block storage. You can also specify your own VCN or virtual cloud network and set max runtime. The maximum allowed runtime for a job run is 30 days, after which the job will be automatically terminated. A job run is the actual processor that executes the instructions in the artifact and follows the parameters set in a job and a job run. For each job run, data science provisions the infrastructure, runs the job artifact, and deprovisions the infrastructure when the run completes. Configurations, environment variables, and CLI arguments can be customized for each job run. During the life cycle, the job run can be monitored, and you can enable logging for each run. A single job can have several sequential or simultaneous job runs with different parameters. This lets you experiment with how the same model training process performs, for example, by providing different hyperparameters. A job run ends when the code ends or triggers the programming language specific exit function. The job run also ends and the infrastructure is destroyed when you cancel a job run. Here is the entire job lifecycle. We've already discussed creating and running jobs, which are the left two columns. The next step in the life cycle is the monitoring and logging, which includes compute metrics and service and custom logging. You will hear more about this in the later lessons. The last step in the job lifecycle is completing or canceling a job, either of which triggers the deprovisioning process and triggers any follow-on events. Jobs can be run in multiple ways and accept a few different types of artifacts. For simpler projects that have single file, you can use Python or Bash. Job runs already provide Python pre-installed. They can run the code with all Python system libraries, including any third-party libraries you've installed. Running your job in Conda environment gives you control and encapsulates all the third-party Python dependency your job run requires, like NumPy, Dask, or HDBoost. Bash and shell scripts are running using Oracle Linux. If your project is more complex and requires more code than is visible in a single file, you can use zip or tar file. If you have complex Python project and shell script, you can archive the entire body of content and run it as a job that leverages either data science service or custom Conda environments. The zip or the compressed tar artifacts can also have a runtime YAML file that sets the required job run environment variables. For the job run, you point to the main entry file using the job run entry point environment variable. This variable is used only with jobs that use zip or compressed job artifacts. Jobs and job runs both support several options for access and management. As long as the proper policy is in place, jobs can access all OCI resources in your tenancy, like data in ADW or object storage. Jobs can also access internal sources if you have configured the appropriate virtual cloud network. You can use vaults to provide a secure way to authenticate against third-party resources. Jobs support OCI SDK and an API. You can run jobs from all possible third-party services, including your client machine, MLOps, Bitbucket, GitHub, or other CI/CD pipelines. You can create jobs and start job runs in OCI console, but you can also create and run jobs with OCI CLI or several languages including Python, Java, JavaScript, Go, Ruby, or Terraform. Job service is essential for running batch inferences. Batch inference is an asynchronous process that bases its predictions on batch of observations or data. Large datasets could be stored in object storage or Oracle database. A new job could be triggered when new data becomes available or at certain interval, say every hour or once a day, to analyze the new data that comes in. Results could be stored back in object storage, databases, or any other desired location. Sometimes so much data comes in, or it must be processed so quickly that a mini batch is preferable. This is a set of more frequent job runs that processes a small amount of data at a time. A good example of when to use a mini batch is a bank analyzing transactions to search for fraud. Every several minutes, a job is run that takes data from the transaction database and looks for fraudulent transactions. An alarm is triggered if fraud is found, and it is handled promptly. In this instance, you don't want to wait for millions of transactions to accumulate. it is a lot of data to analyze and slows down the fraud detection process. Many batch jobs like this are often executed with cron scheduler or based on some processes or events that triggers the job. Again, results from the batch processing could be stored in databases, object storage, or any other location. A third batch option is distributed batch. In this case, there is a large amount of data that can be split into several chunks, and multiple models and jobs can run simultaneously for faster processing. Each of these tasks or jobs can be executed independently without any dependencies between them. These are also called embarrassing parallel jobs. This table compares the attributes of the three types of batch inferences: regular, mini, or distributed. The main differences are the size of the infrastructure, workload, and process time, with mini batches being small and short, and distributed batches usually being large and long. Regular batch jobs are somewhere in between those two extremes. In addition to running different types of batch jobs, another way to decrease the runtime of jobs is to scale your compute and storage resources in the data science service. To do this, you must edit the compute shape and block storage. You can scale up or down the compute shape and block storage size in your job, as well as in your notebook session. To recap, in this session, we learn about data science jobs basics, when and how to use it, and how it enables MLOps. We've shown how easy it is to access the service and use it from third-party software. We demonstrate the different types of batch processes that are possible using the service. In this demo, we would learn how to create a job artifact to use with your jobs. The artifact can be a single Python file that contains the code to run as a job, or it could be a single scripts file. Additionally, you could run an entire Python project as a job by compressing the project directory into a zip file and upload it as a job artifact. There aren't special requirements of how to write your Python or shell script, and in this demo, we will demonstrate a simple single Python file job artifact. So let's start our job artifact with two simple lines of Python code, and we are going to extend it down the line. We have just two prints here indicating that the job is starting and the job is finished. So let's add additional code to make this a little bit more useful for our demonstration purposes. So here we extended the code by changing the first print to print something like a timestamp to indicate when our job has started. So as next, let's see how we can read environment variables and command line arguments. We extended the code to read environment variable that it's called name. As you can see, reading environment variables in Python code, it uses the standard libraries. We do not enforce specific requirements. And then we include a new print line, which is printing the name that we are going to pass as an environment variable. So next, let's see how to read also command line arguments. So we included also a code to read the command line arguments. As you can see, it's a standard Python code. We expect to have a command line variable. We expect to have a command line argument called greeting or short -g. And then we change also the line here that it's printing our greeting additionally with the name that we were printing before. So this is a very simple job artifact example. As you can see, this is a standard Python code. We do not enforce or have some specific requirements of how to write your Python code to run it as a job. What you see now is a little bit more extended version of the same code, which is now also including the ability to use the Python OCI SDK. The code can be run locally to test first that your Python code works properly before you run as a job. Resource principle is the Oracle Cloud Infrastructure authentication mechanism to provide permissions to your cloud native resources to access services or other resources from your tenancy. This code is the same as the previous one with the extension of this piece here, which switches between your local environment or identifies when the code runs as a job and then starts to run the resource principle. It has, however, the same command line argument and expects the same variable, which is going to be printed here. Additionally, we are showing also a very simple example of how to use the OCI SDK. And this is the code that we are going to use in the rest of our demonstrations. In the next part of the demo, you will see how to create and run job using this code. Now that we have our job artifact ready, we're going to review how to create and manage jobs. Log into your Oracle Cloud tenancy and locate the data science service. You can find the data science service from the hamburger menu here on the top left side under Analytics and AI, and it appears under Machine Learning. Create a project in case you don't have one. To create a project, just click on Create Project button, provide a name and description, and then click on Create. In our case, we have already project created and we're going to use it to create our jobs. Within my project, on the left side, I see the different resources that the data science service provide. Notebook sessions, jobs, model catalog, and model deployment. To create job, we're going to select the jobs resource. Click on Create Job. And from the new screen, you have the option to change the compartment. If you'd like to create the job in a different compartment, you can set job name, which is optional. The job will create name by default. You can have also description for the job. And as next, we have to select and upload our job artifact. This is the Python file that we created in a previous step. Click on select a file, select the file from your computer and click open, and this is going to upload the file. Using the console, we have a upload limit from a file that can be maximum 100 megabytes, but if you use the OCI SDK, you can upload larger artifacts. Next, on job creation, we can set the environment variables. In our case, we were expecting environment variable code name. Let's provide a value, and our code also expects a command line argument, which was for the greeting, -G, hi. Here we can set up also the max runtime in minutes, for example 100. Next we have the option to select compute shape. Oracle Data Science Service job supports two types of compute shapes. Shapes enabled for fast launch and custom configuration. The fast launch shapes are shapes that exist in pre-warm pool and can launch and execute your code very quickly. Fast launch supports only pre-selected enable shapes. Oracle Data Science Service can expand the fast launch pre-warm shapes depending on customer needs. Under custom configuration, you can select additionally GPU shapes or Intel shapes that are not into the fast launch pool. Next, we can select logging. Logging is optional but recommended. For example, all STD out or STD errors, if logging is enabled, will be automatically sent to our OCI logging service. To enable logging, click on select and then select the log group into which you want to create your logs. And you have two options to automatically enable log creation on every job run or select log that was previously created. In our case, we're going to use the option for automatic log creation. Click on select. Next, we have to set up the storage. This option is very important. This is going to be the block storage that will be automatically created and attached to your job. Make sure that the size of the storage corresponds to the need of your batch processing. Next, we have the option to select networking resources. You can select default networking resources with which you don't have to create virtual cloud network and subnet. It will automatically provide you access to the internet and to the most of the Oracle Cloud Service. For more advanced configurations, you can create your own virtual cloud network and subnet and use the custom network option to select them. In our case, we are going to go with the default network as we don't have some special requirements to the virtual cloud network. Once all those configurations are done, click on create, and this is going to create your job. Now that the job is created, you can review the job information, like the general information, when was the job created, the job artifact, the logging configuration, as well as the infrastructure configuration. This is just a job specification. This job is not running yet. This is going to be done by executing a job run. Additionally, we can review the job configurations, in our case the command line arguments, the max runtime in minutes, which is the time after which the job will be automatically cancelled if the job didn't finish in the selected time, and custom environment variables. You have the ability to edit the job after the creation. To do so, click on the edit, and here you can change the name of the job as well as adding some description. You can also change the compute shape, the storage, and click save to save your changes. You can also download your artifact. Just click on a download artifact, select the location of where you want to store your job artifact and click save. You can move the resource to a different compartment, or you can add additional tagging or delete the job. In this demo, we're going to see how we can start and manage job runs. My name is Ludmil Pelov, and I'm a product manager in the Oracle Data Science and AI Services team. Now that we have our job created, we can execute one or several job runs at the same time if you want to. To start the job runs, we have to click on Start a Job Run button using the OCI console. And in the table here, you can see job runs that you run in the past. In case that the job failed, you will see the status and the lifecycle detail, as well as who created or run that job and the time the job was accepted for running. So let's see how we can start our own job run. As I mentioned, to be able to do so, you just have to click on Start a Job Run. And we will get a new screen where we can adjust some of the settings. The first one is we can change the login configurations from the default we set when we were creating the job. Here, if you want, you can adjust and you can either disable logging, or you can set a new log group, or you can set a log instead of enabling the automatic log creation. Additionally, you can also override custom environment variables or set a new one. You can also set new command lines and set the maximum runtime. So let's say that we want to set up a new environment variable that it's called name that our code is using, and we maybe want to adjust the greeting to hey, and then we click on Start to start a job run. It takes a few seconds for the job run to transfer to accepted state. And then we will see a message appears which identifies that the infrastructure for the job is in provisioning state. This is where we going to see the different life cycles of the job where the job will automatically provision the infrastructure that we set up. And we can see here on the right side, it's going to provision the code, the artifact that we specified, and the job is going to execute it. And then the last life cycle where the job is going to deprovision the infrastructure so that the customer pays only during the duration of the execution of the artifact. We can also track the process of our job looking into the table. It is also very important to notice that you don't have to wait for this job to finish to start a new one. Imagine that you are having a model training job and you would like to be able to explore different settings. During the execution of the job that we've just started, we can click on Start a Job Run. We can set new environment variables or command line arguments, and we can start a new job. All these jobs can run then in parallel at the same time. Now we can see how the job lifecycle change, and we're in job run artifact execution, which is in progress. In case that the job artifact execution failed, as we can see right now here, you can again click on your job run and then on a log file. And here you can discover what the problem was and why the job failed and try to fix that problem. Once the job is done, we also have the ability to do some changes to the job. For example, if I select this job, I can edit the name of the job if I want to, or I can set up a new tags. One ability that it's only available in the OCI web interface console is the ability to clone job run. If you click on clone, if you are having custom environment variables set before and command line arguments, all those are going to be automatically provisioned, and so that you can only change the values that you really need to. Deleting a job is very easy. For example, the job that we have right now here, if you want to delete it, just click on delete. You're going to get a confirmation message where you can confirm again that you would like to delete this job. And now the job is going to be automatically deleted. Additional feature in job run is that we can cancel the job before the job finished. So let's start a new job run and see how the cancellation works. We're going to start a new job run by cloning a job that was successful before. I'm not going to change any of the settings here. If you want to set up a new name or just update the timestamp of the name, you can remove the one that was previously there and click on Clone Job Run. Now, as you can see, the job is preparing to start, but the cancel button is now activated. At any point of the job run execution, we can cancel the job if we think that we made a mistake or for some other reasons. Clicking on a cancel button, it's going to stop the job immediately at any state of the job during the provisioning of the job infrastructure or during the execution of the artifact. So let me click on cancel, and as you can see in the UI specifically, you have to confirm the cancellation of the job run. Just click confirm, and now the job is going to be cancelled. Notice that metering is also going to stop with the cancellation of the job, so that you are not going to continue to pay when the job is cancelled. In this demo, we are going to learn how to scale up and down jobs and notebooks in Oracle Cloud Data Science Service. My name is Ludmil Pelov, and I'm a product manager in the Oracle Data Science and AI Services team. In the case where you had a job run and you identified that your CPU, storage, or memory utilization was very high, you have the option to change those by editing your job. To edit your job, just select the job and then click on the edit button. Here you will see that you can change the compute shape. You can either go for a Fastland shape or you can select one of the other standard shapes. In my case, I was using VM Standard 2.1, which is the smallest possible shape when you run jobs. If you click on Shape Shape, I now have the ability to select a shape that is having more OCPUs and more memory. Or in cases where I'm doing model training that will benefit from GPU, I can go and select one of the data science service available GPU shapes. Additionally, I can also change the size of my storage if I notice that the storage that I was using before is not sufficient enough. Once I have all my settings done, I just click on Save Changes. And I can start a new job run that is going to immediately utilize the new infrastructure configurations. Let me show you also how you can scale up your notebook session. If you click on your notebook, you can monitor the notebook metrics in a similar way we do for jobs. For example, you can monitor your CPU or memory utilization, and if you notice that your current instance shape is not good enough or it's utilized to the max, you can scale up your notebook. What is important for notebooks, however, is that before you're able to scale the notebook, you have to deactivate the notebook first. You have to click on the deactivate button and then confirm the deactivation by clicking on the deactivate in the confirmation window. Notice that the deactivation of the notebook is going to stop also the metering or the billing of the notebook, but it's not going to remove the block storage, which means all the data you had on the block storage and you're using for your working are not going to be deleted. Now that my notebook is inactive or deactivated, I can start my notebook again, and on activation process, I can change the compute shape and the block storage size. To activate my notebook, I just click on the activate button. And here now I have the opportunity to select one of the available notebook shapes. I can select the Intel shape that is having more OCPUs on memory. I can go for one of our flex shapes, or I can select a GPU shape. Let's say that in my case, I'm just going to get a Intel shape that it's having more OCPU and more memory. Select that shape. And here I also have the ability again to increase the size of the block storage. With this, I can just click now on activate, and my notebook is going to start with my new compute instance shape and block storage size. Notice again that the work and the files that I had on my block storage is not going to be removed, and I can continue working with it just as before I deactivated my notebook.